Hello students, welcome you all. In my today's lecture, I will explain you the regioselectivity and stereoselectivity in Diels-Alder reaction. In my previous lecture, I told you about the endoselectivity or endo rule which is followed in Diels-Alder reaction, where the endo product is preferred over the exo product. So here I will explain you the intermolecular Diels-Alder reaction and intramolecular Diels-Alder reaction where regioselective or stereoselective products are formed. So if you see the simplest is example of this Diels-Alder reaction where this butadiene, it reacts with the ethylene system to give the cyclohexene, okay, and this cyclic shift of electron. And this reaction, it is favored under the thermal condition where the superficial addition takes place, or we can say this is 4s plus 2s system. So what was this rule for this selection rule for this cycloaddition reaction? So if you will see, I have discussed the selection rule for cycloaddition reaction, that is for 4n electron system and for 4n plus 2 electron system. So under thermal condition, what we saw, under thermal condition, the superficial interfacial interaction takes place between the 2 pi system or the interfacial superficial interaction that we may write. Whereas under photochemical condition, superficial interaction takes place between the 2 pi systems or between the 2 pi component. Here the superficial for 4n plus 2 electron system under thermal condition, superficial interaction occur, whereas under photochemical condition, superficial interfacial or intrafacial superficial interaction takes place. Okay, so here this is 4n plus 2 electron system where the 6 pi electrons are involved here in the reaction. So in this reaction 4s plus 2s addition will occur, that is superficial for this one as well as the superficial for this one. So both component will react superficially. Now, so these two systems, so this is 4 pi system, this is 2 pi system. As this is 4 pi system, 4 pi electrons are present. That's why this is electron rich, and this is electron deficient. So the diene is electron rich, whereas dienophile is electron deficient. So that's why this should act as a HOMO and this should act as a LUMO. So the reactivity of this Diels-Alder reaction, this increases if the electron withdrawing group, if the electron releasing group or electron donating group is present over the diene. So if electron donating group is present over the diene, then it will become more electron rich. Whereas if electron withdrawing group is present over the dienophile, then it will become more electron deficient. So what I mean to say, that we should make this diene more electron rich and this dienophile more electron deficient, so that the reactivity of this Diels-Alder reaction increases. So we can add, in presence of, suppose if we have some electron donating group here, then it will become more electron rich and reactivity will increase. Similarly, if we have any electron withdrawing group, suppose this is the electron withdrawing group, so electron withdrawing group, then it will become more electron deficient and reactivity for this Diels-Alder reaction that will increase. So this electron withdrawing group, there is two possibility that the electron withdrawing group may be present at this terminal carbon or it may be present at this middle carbon. So I may take two cases. Suppose case number 1, if electron donating group in diene is present at terminal carbon. Suppose if it is present at terminal carbon, okay, then, so let's see, suppose if we have electron donating group which is present over here. Suppose electron donating group, this is methoxy group which is electron donating group. This has the lone pair of electron, so it can easily donate its electron. And suppose if we have some electron withdrawing group at the dienophile. So electron withdrawing group at the dienophile, either we can write here or here. Okay, so only the terminal positions are there in this diene and dienophile. There is no middle carbon in the dienophile. So either I may write the electron withdrawing group either here, or we may write the here. So suppose I write the electron withdrawing group over here, that is suppose CHO. This carbonyl, for example, either aldehyde or this ketone or some ester group, they may act as a nitro group, they may act as an electron withdrawing group. Now, so what should be the product here? If the electron donating group is present at terminal carbon over here, and what should be the product? So in this case, if we want to write the product, then we can understand it in two ways. One way by push and pull mechanism, push and pull of electron mechanism. So if you will see here, then this electron may come over here, okay, and this will go over here, and this should go at this place. This will like this. So what you can see here, so if you will see the intermediate which is formed over here, then double bond will come at this here position, plus charge will come over the oxygen, and like this. Now you can see the new double bond is formed over here, new pi bond over here. This is converted into single bond, and one of the new sigma bond is formed between this one and this one. New sigma bond is formed, and here this will become the single bond, and now this becomes the double bond, carbon atom, oxygen minus, and having this, okay, sorry. So like this. So we have an intermediate which is having one of the positive and the negative charge, so this should be neutralized. In next step, this should neutralize, and how this will go over here, okay, and this comes over here, this positive charge is also neutralized. What we have, you can see, you may see the final product which is formed, this methoxy group, it is present over here, and this aldehyde group is present over here, CHO. So you may see the ortho product is formed. This is the ortho product. You may see the ortho product. Now you may understand this also in another way. Suppose if here, and this will have the negative charge, no doubt, and because this is the electron withdrawing group, that's why it should have the positive charge. So now join directly, you may join directly, the positive negative join directly, and you may write the product also. Okay, so just write this one. So this will negative charge, this is positive charge, join it, this join this one, and you may write that directly. So otherwise you may understand this mechanism by electron push and pull mechanism. So now case 2, where this electron and donating group is present at this middle carbon. So if electron donating group in diene is present at inner carbon, you can say, or middle carbon. Better to write inner carbon. Okay, so in this case, now at this diene, electron withdrawing, electron donating group is present at the middle carbon. This is our dienophile, and here the one of the electron withdrawing group is present over here. Okay. Now, so if you will see here, then again we may understand it by push and pull electron mechanism. So this will go over here. Now this carbon, the valency is increased, that's why here this bond, this pi bond, this will break, and here you may see this will can go over here, and this will go over here, and this will. Okay, so what you can see, you may see a new sigma bond is formed over here, new sigma bond. One of the, this has become double bond, oxygen having this positive charge, this is having the double bond, and this double bond is converted into the single bond. You have a double bond, new double bond is formed over here, and negative charge. So in next step, this positive negative charge that will get neutralized. Again this pi bond is restored. Okay, and this will go over here, and we will get this product. Okay. So what kind of product you may see? Here we have got the para product. We have got the para product. Okay. So overall what we have seen, now this can also be understood, suppose and this will having the, this may have the negative charge, because if this electron comes over here, then this will go over here, this is, and this will having the negative charge, and this should have the plus charge. You may join this plus minus charge and you will get this product. So this is another way that we may do. Okay. Now, so overall what we have seen here, the only the either ortho product is formed or para product is formed. So in this case, in this Diels-Alder reaction, you will not find any meta product, either ortho product or para product is formed. So if the electron donating group on the diene is present at the terminal carbon, and you should remember, if electron donating group on diene is present at the terminal carbon, then always ortho product would be formed. If electron donating group is present over the middle carbon in diene, then always you will get the para product. That you should remember. So no note, you may write the note, meta product is not formed. Meta product is never formed. Is never formed. Okay. So like this. So this is the in this way we can get the product for this intermolecular Diels-Alder reaction. So this is an example of intermolecular Diels-Alder reaction, and where this there are the two components which are present in the system. Now, suppose if we have suppose this is diene, and we have one of the electron donating group. Okay, triethylamine, this electron donating group, this is the electron donating group, and suppose if you have ester group. So ester group is electron withdrawing group, which is present over this dienophile. And then what should be the product? Product you may write what I have told you. If the electron donating group is present at the terminal carbon, then always we get the ortho product according to that mechanism. So you may write directly, you may write the ortho product. So here you have this group, and to ortho to this you will get, you should write COO and ester group like this. Okay, so this should be the product. In this way, by following that rule, you may write the product directly. So now let's see the intramolecular Diels-Alder reaction. Suppose if you see the intramolecular Diels-Alder reaction. Now let us explain the intramolecular Diels-Alder reaction. Where this dyne and dienophile, they are present in the same molecule, or you can say they are present in only one component is there. So suppose okay, now if you will see here, then one of this dyne component, this is the dyne component, and this is your dienophile component. Okay, now what should be the product formed? The product formed, the cyclic shift of electron again, and you will see the two rings similar to this Decalin type of system, and one of the new double bond is formed over here. This is the one of the new double bond. This is new sigma bond is formed. So sigma bond is formed. You can see this is one of the sigma bond, and here another sigma bond is formed over here. According to the cyclo addition, and this is cyclo addition reaction. All of you know the 2 pi bond is decreases in product, and two new sigma bond is formed. Okay, two new sigma bond is formed in the cyclo addition reaction. Okay. Now, so here in this example, there is what I told you, the dyne that should have the electron donating group, and the dienophile that should have the electron withdrawing group, so that the reaction, the reactivity in that case, that increases. So in this case, there is no electron withdrawing group which is present over this dienophile. No electron withdrawing group is present. So what should be the product in this case? Means we may take this as the first case number 1. Case number 1, when no electron withdrawing group is present on the dienophile. This is case number 1. Okay. Now, so in this case, we should see for the stereochemistry of hydrogen at the fused carbon. So these are the fused carbon, and what should be the stereochemistry at this fused carbon? So we can consider similar to this Decalin system, where the trans product is favored over the cis product. So no doubt at this position, the trans, this should be the trans product, means the 2 hydrogen atom that should be trans to each other. So this is the case when there is no electron withdrawing group over the dienophile. Now suppose electron withdrawing group is present over the dienophile. Now the electron withdrawing group, either this may be present at this carbon, this is one of the case, which I may call it as a inner carbon. Okay. Or the electron withdrawing group may be present at the terminal carbon. So there may be only 2 cases. Either the electron withdrawing group may be present at this inner carbon, or the electron withdrawing group is present over the terminal carbon of the dienophile. Now, so suppose I take the second case, when the electron withdrawing group is present at the inner carbon atom. Of dienophile. Okay, then what should be the stereochemistry of hydrogen at this junction point, at this fusion point? So Now, suppose I write one of the electron, I add one of the electron withdrawing group at this inner carbon. So this is our inner carbon, one of the carbonyl group is present over here. Now, so what should be the stereochemistry? What should be the stereochemistry of hydrogen at this point? Now, at the junction point. So no doubt the cyclic shift of electron, and you may see two new sigma bond and one new pi bond is formed. Okay, so this is one of the new pi bond, and this should be the position of the electron withdrawing group. Now, what should be the stereochemistry of the hydrogen at this junction point? Now, so what I told you in my last lecture about the endo rule. So in endo rule, what this endo rule tells, the electron withdrawing group that should be the endo to the double bond. So for example, if you have this one, this diene, and one of this group is present. This is the electron withdrawing group which is present over the dienophile. Then what kind of product that you should get? You will get here, and always this electron withdrawing group that should be below. That should be below. That is, it should be closer to this double bond, so that a secondary interaction may occur. Or we can simply, in a simple way, you may write like this. In a simple way, you may write the electron withdrawing group like this one. So always this should be represented in dash form, not in wedge form. So always this should be represented in dash form, means it is below. It is going below, so that it is closer to this cavity, or we can say it is closer to this double bond, so that the secondary interaction can occur. That I told you in my last lecture. So that's why if electron withdrawing group is present over here at this, it means that should go below. So this electron withdrawing group should always go below. So that's why you may write, it means this ring will go down. This ring will go down, so that it may get interact with this double bond, so that this electron withdrawing group may interact with this double bond. So that's why you can write like this. So this ring is going down, means it is endo to this double bond. The electron withdrawing group is now endo to this double bond. So if this is going down, if ring is going down, then the another group, that is the hydrogen, another substituent which is the hydrogen over this carbon, that no doubt that should be above. That should always be above. And this is also going down, and that should also be above the plane. So this should be the stereochemistry. This should be the stereochemistry of the two substituent or hydrogen over this fusion point. Okay, so hope you will understand. So what I am telling you, if any electron withdrawing group is present over the dienophile, then that should be go below, according to this endo rule. That should be go below, so that it may get interact with this two new double bond which is formed over here. And if it is going below, then no doubt this hydrogen atom, this substituent atom, that should be go above. So this is the case when electron withdrawing group is present at the inner carbon atom. It is present at the inner carbon atom. So this electron withdrawing group may be present at this terminal carbon atom or this outer carbon atom. So now case number 3, if you will see, when electron withdrawing group is present at the terminal carbon atom, of dienophile. Okay, then in this case, let's see, suppose in the case number A, this again now Now, so this is a terminal carbon atom, and suppose the electron withdrawing group is present like this, COO, and ester group is present at this dienophile, and this is our dyne, this is the dienophile. Now, what should be the product in this case? What should be the product in this case? Now, what I have told you? I have told you that always the electron withdrawing group at the dienophile, which is present at the dienophile, that should go below. That should go below so that it may get interact with the new double bond which is formed over here. So, suppose these two rings, you may take two rings here, and one new double bond is formed over here. Now, so this is the electron withdrawing group which is present over this carbon. Now the electron withdrawing group is present over this carbon. So what should be the stereochemistry of this electron withdrawing group? No doubt that should be go below according to this endo rule. So first of all you should write this is going below CO. Now if it is going below, then the hydrogen here, the hydrogen which is present here at this fusion carbon or this point, so hydrogen is no doubt it is cis to this electron withdrawing group. So hydrogen is cis to electron withdrawing group. That's why the position of this hydrogen that should be like this. It should be cis to this, because here you may see the hydrogen is cis to this electron withdrawing group. So in product also we should write the hydrogen cis to this electron withdrawing group. And the another, so here either the hydrogen at this carbon, either it may be in the same, it may go below or it may go above. So in this case you will see two products would be formed. Now the position of these two groups here, the position of these two, that remains same. So this remains same. We may say that this is a stereospecific addition, so this remains same, but either this hydrogen, either it may go below or it will go above. Okay, so this is the case. Now suppose here the electron withdrawing group is present trans to this hydrogen. Another case that we may take, the electron withdrawing group, it may be trans to this hydrogen. So suppose if you take trans, then what should be the product? Now, you may see that now the electron withdrawing group is present trans to this hydrogen. So this hydrogen which is present, this is trans to it. So here it was cis, here it is trans. This is the next phase. Now the product that you will write, so again you may see same thing, cyclic shift of electron and new double bond over here. This is the two new sigma bond which is formed. Now this electron withdrawing group which is present over the dienophile, no doubt according to this endo rule, that should go down. So that should go down. So I should always write like this. According to this endo rule, this should always go down so that it may interact with this pi bond. And now if this is down, then this should be up, because these two are trans to each other. So that's why the hydrogen which is present at this junction point, that should be trans. This is trans. Okay. Now, so this hydrogen at this carbon, either it may be above or it may be below. So in this case, when the electron withdrawing group is present at the terminal carbon atom, then you will see two products. You will see the two products. Like this. So either Here the hydrogen it may be go above or it may go below. So what you have seen, if electron withdrawing group is present at the terminal carbon, then two products are formed, whereas the position of this remains same. The position of this remains same. Here the stereospecific addition, this is a stereospecific, but overall if you will see, then the two products are formed like this. So this is about the intramolecular Diels-Seyde reaction, and we may write the sum of this regioselective or stereoselective product over here. Thank you.